Colloids and confocal microscopy. I'm Dave Waits, and I'm going to pick up where I left at the end of last lecture and try to continue with as much as I can get through of what I have planned for today. So we were talking about colloidal aggregation last time, and we looked at the formation of the clusters. And we were discussing how the degree of tenuousness of the clusters depending on how they're formed. And we said that there were three important dimensions. The dimension of space, and generally speaking we're going to be in 3 dimensions. The dimension of the clusters, the fractal clusters, that is their fractal dimension, and the dimension of their trajectory. And I'm looking at slide 3 here, I'm showing how this plays a role, and you can understand it qualitatively just by looking at these figures. Let me get my drawing thing. If I look at this upper figure here, you have 2 fractal clusters, and let's say they are formed with the same way as I showed you with the diffusion-limited clusters, so their fractal dimension is 1.75. And they are diffusing. They are themselves diffusing. So the center of mass, say, of the cluster on the right undergoes this random diffusive motion here. And because of the diffusive motion, this cluster is going to hit on the outside of this cluster. And so you can see that they're going to stick. The 2 tips of the clusters of one cluster will stick to the tip of another cluster. And that will lead to a very tenuous open structure. And you can see this by summing the fractal dimensions of the 2 clusters, so that's 1.75 and 1.75, plus the fractal dimension of the trajectory, which is 2, and that ends up being much greater than the dimension of space. So if that's the case, what that says essentially is that the 2 clusters can't interpenetrate. Now let's compare that to the case where you have one of the clusters being a point, just a single particle, and the other cluster being a fractal cluster, again with a fractal dimension of 1.75. And again, imagine that it's a diffusive motion. So these are, in some sense, the 2 limits. You have 2 clusters that are the same size, or one cluster trying to aggregate with a very small cluster, and the limit of the small cluster is a monomer. So the fractal dimension of a monomer is 0. It has no dimension. So in this case, we have the fractal dimension of the first cluster, that's 1.75, the fractal dimension of the second, that's 0, and the fractal dimension of the trajectory, that's 2. That still is greater than the dimension of space. And what that says is that this particle that's undergoing a random walk, is going to be trapped at the outside of this cluster. In fact, this is the heart of what's commonly called diffusion-limited aggregation, which is a growing aggregate where you add only a monomer at a time, but the monomer sticks upon contact and undergoes a diffusive motion. And that leads to these very fractal-like structures. In 2 dimensions, you'll get a slightly different fractal dimension, but the physics is essentially the same, that you don't get penetration. Notice, however, that if you start with a monomer and you had this chemically limited aggregation. That is, this can diffuse all at once, but it takes so many times. It's such a nearly stable system. It takes so many times for collisions to occur that it's very rare that things stick. It's a very rare occurrence. Then it doesn't stick when it first hits. It can basically explore all of space. And therefore, it's like having a trajectory also of 0. In that case, you would have a fractal dimension of the first cluster, say, of 1.75, but then it would be 0 plus 0. And since 1.75 is less than that of space, that means that the single particle can penetrate the fractal dimension of the cluster, and essentially that means that you'll get a much denser cluster, and that's exactly what you see when you have reaction-limited aggregation, that you get denser clusters. The fractal dimension goes up. Okay, Now we can go to the time evolution of this, and we can describe the time evolution in a number of ways. The most common way, a rather successful way of describing it, is through the Smoluchowski equation. These are essentially a set of rate equations. It's shown here. It's asking if you imagine a distribution of clusters of mass m. N is the number of clusters of mass m, and you just ask how the number of clusters with a given mass changes as a function of time. And this m can go from 1 up to as large as it gets. And so this depends on the rate of breakup and the rate of addition. So here the first term is you're summing all clusters that sum to I, all different clusters, pairs of clusters, j and I minus j. This is the rate of aggregation. You're summing all the aggregating clusters, and that's increasing the number of clusters, and you're decreasing it by a rate of breakup, or a rate of loss in this case. Say a cluster of I aggregates with a cluster, collides and sticks to a cluster of j. That means you remove it from the distribution of mass I, and you go to the distribution of mass I plus j. So this is the sum of the formation minus the sum of the loss. And this is just a series of an infinite series of rate equations, just second order differential or first order differential equations, and you just have to sum these things. You can use these expressions to look at the behavior experimentally of the mass distribution. Here's some experiments how you might do this. These are just images, EM images of an aggregating system. Again, it's an aggregating system of colloidal gold. And this is just a snapshot showing the different clusters, and you can go and just simply count the number of clusters of a given mass and form that distribution. If you do that for reaction-limited conditions, that is, for diffusion-limited conditions, that is, reactions occur immediately upon collision, you get these kinds of distributions. This is as a function of time. At early times, you have, this is the logarithm of the distribution, the number of clusters of mass I as a function of mass I, normalized to the total number of particles, and you see that they look, roughly speaking, flat with some cutoff. It's actually flat with an exponential cutoff. And indeed, you can take all of these distributions and you can scale them and scale them together and plot one common distribution. And this common distribution, the cutoff value changes with time, but the shape of the distribution remains the same. It's essentially flat at low masses with some exponential cutoff. If you do the same experiment now for reaction-limited conditions, that's shown in image B on the right here, you see that, first of all, there are many, many more small particles, and the large clusters are large but much more dense because you can barely see through them. That reflects, of course, the fact that the fractal dimension is increased, and the large number of very small clusters, by comparison to here, reflects the fact that the distribution is actually much broader. It's a much wider distribution, and that's shown quantitatively here, where again the distributions are plotted as a function of time, and you can see now we're plotting them in the log-log plot, and they are essentially a power law with ultimately some exponential cutoff. They're a power law. The slope of this is minus 1.5. Again, they all scale together, as shown in this insert. They all scale together. The only thing that changes is the cutoff value, but you get this power law distribution. You can understand the origin of this distribution. There's a nice theoretical paper by Robin Ball that describes the origin. The value of 1.5 turns out to be something that you can analytically predict, that you have to have this value for this type of aggregation. And you can predict the scaling, the shapes of these scaling behaviors, this minus 1.5, and indeed, if I go back here, the shape of the shape that you get for the scaling behavior and the flat distributions here, those can be predicted with this mean field Smoluchowski equation description. If you look at the value of the average or the cutoff cluster and plot its behavior as a function of time, you see experimentally that for diffusion limit aggregation, this is shown for a variety of different colloidal systems. It doesn't depend on the system. You always get this linear growth in time. This is a linear plot where you're plotting the sorry, this is a log-log plot, but it doesn't matter. It's linear growth in time, plotting the cutoff size as a function of the aggregation time, and you get this linear behavior. And again, this is absolutely what is predicted by the mean field description, the Smoluchowski description. If you look at the reaction limited case, you see that it asymptotically becomes exponential. This is the logarithm of the size as a function of time, so this is exponential behavior. So what this says is that there's some induction time, and then it grows exponentially. And the reason it's growing exponentially is that the dominant growth comes from the larger clusters sticking together. That's where the main contribution to the sizes. The small clusters really don't contribute that much to the average. Even though there are many small clusters, they're so small that when you calculate the average, they don't contribute much. So you just have to look at how the largest clusters are growing, and they're getting, even though they're reaction limited, they're getting faster and faster because they're larger. So there's more contact area. There's more opportunities for them to stick together. You can learn a lot more about these by doing scattering from them. Neutron scattering works very well. Sunny Sinha has done some beautiful neutron scattering experiments from fractal clusters, fractal aggregates. Light scattering also works well. Colloidal particles tend to be somewhat larger, so you'd have to go to ultra small angle neutron scattering, or you go to light scattering. There you can do it at the more traditional angles. You can understand the static scattering, and this is valid for static scattering of any wave, whether it's neutrons or X-rays or light. You can understand the static scattering from a fractal object in a very simple fashion. Here's the nature of a fractal object. It's got this very tenuous structure, and at any angle, any value of a wave vector, you're looking in a volume that's made up of 1 over the wave vector, that's a length, 1 over the wave vector cubed. Within that volume, you have no resolution of the structure. Within that volume, the scattering is essentially coherent, and therefore varies. The intensity of the scattering depends on the square of the mass inside that volume. But outside that volume, at length scales larger than 1 over q, then you no longer have complete coherence, and you have to do interference between the objects of larger length scales. And if we say the simplest way is that they just add linearly, they don't add coherently, so you get lots of cancellations, you just get some linear addition, then you can easily calculate the scattering intensity. The scattering intensity is just the number of regions of this size, because they're adding linearly, each of them adding linearly, times the square of the mass inside this size, because that's coherent scattering. So the coherent scattering goes as the square of the mass. So I just take the intensity from this, which goes as the square of the mass, and I sum up the number of regions of that size. So the number of regions of that size is just the total mass divided by the mass in each of these. And then I have to multiply by the square of the mass in one of these things. That's what's shown here. So this becomes the total mass times the mass in one of these regions. The mass in one of these regions is proportional to the radius of that region to the fractal dimension, and the radius is inversely proportional to the wave vector, so it's just the total mass divided by the wave vector to the fractal dimension. So this says that the static scattering should decay as 1 over the wave vector to the fractal dimension. And this is traditional for scattering. And if you have a distribution of clusters, then you can do this more formally, and you sum over the distribution, but with the same form factor. So this is the form factor that I showed, and then you just sum over the distribution like that. And this actually works quite well. Here's a light scattering from fractal clusters that are formed by diffusion-limited aggregation. Diffusion-limited aggregation, remember I showed you, had a fractal dimension of around 1.75. In fact, I would say more generally it's around 1.8. And here are these scattering from different colloid systems. These are large clusters, and you see that they have the scattering, the Q dependence of the scattering is 1 over the wave vector to the 1.85, or 1 over the fractal Q vector to the fractal dimension. And similarly, for clusters that are formed by reaction-limited aggregation, there we said that the fractal dimension is somewhat larger. It's a little bit over 2. And here you see that they go as a power law 2.1. So this is a very simple way of measuring the fractal dimension of these objects. You can do a lot more with the scattering. I really don't have time to discuss them, but just briefly, here all the clusters are large compared to the smallest value of Q, where the wave vector is the inverse of the wave vector is the largest. So you just see the fractal behavior. If they were not that large, then you would see something that became flat at the lowest wave vectors, because you would not have clusters that are large enough to have a fractal scaling at the very longest length scales. And you can certainly see that. You also can do dynamic light scattering. You can watch the rotation or the translation of these clusters, the diffusion motion. This is something that I believe Ben Chu discussed, the dynamic light scattering. You can do the same thing here. What's interesting in this case is because of the very heterogeneous structure of the fractal, because they have these heterogenees, they have holes on all length scales, because as reflected by this fractal-like behavior, when you do dynamic light scattering, you see a very strong contribution of the rotational motion in addition to the translational motion, and you have to incorporate that into the understanding of the scattering. You have to do the summation over the clusters of fractal in shape that are also rotating. You can do this analytically. Rudy Klein did this a number of years ago. It comes out very nicely, and you can understand really quite well the behavior. Not surprisingly, because the cluster mass distribution exhibits the scaling behavior, and because the structure is scale invariant, the dynamic light scattering also exhibits a lot of scaling kinds of behavior. So let me turn now not to the scattering of these structures, but to the properties of the structures, and in particular, as I discussed before, the importance of colloidal suspensions is the rheological properties. And one of the really important features of the aggregates, you can form colloidal aggregates. They can, as I showed, the mass of the density of the colloidal aggregates gets smaller and smaller as they get larger. That means they fill more and more of space as they get larger. As a result, what happens is, in all cases, if you have a system that's purely growing as fractal objects, eventually you form a system that spans all of space, and you form a gel. And anytime you form a gel, you're going to have both viscous properties but also elastic properties. So what's very interesting about colloids then, in general, is to ask about their elastic properties, and because they're also fluid, their viscoelastic properties. And I'd like to turn to that now to understand something about their behavior. I would like to describe it in a very general terms. We talked about both reaction-limited and diffusion-limited. In the case of reaction-limited, you had a barrier to sticking. Now I'd like to also generalize this, not only that there's a barrier, but also that the sticking doesn't have to be that strong. So the particles can stick to each other, but not with enormous amount of strength to the bond. So let's consider a bond energy normalized to kT, And of course, the other important parameter always in colloidal suspensions is the volume fraction. So we can look at a plot as of the behavior as a function of the bond energy that holds two particles together and the volume fraction. If the bond energy is 0, just along here, then you have hard spheres, and you have the traditional behavior of hard spheres. I won't describe that in detail, but briefly, hard spheres are known. This is one of the great successes of computer simulation. They're known that hard spheres actually crystallize purely for entropic reasons at a volume fraction of around 49%, and they coexist between a crystal and a fluid between 49 and 54%. Above 54%, they're completely crystalline. But for hard spheres, it's just along this line. If you introduce some attractive interaction, that's shown here, some attractive interaction, upwards of attractive interaction. So this is different than what I showed before when I was plotting the stability curve where attraction was negative. In this case, the attraction is positive. I'm plotting on the positive axis. So now we can understand what happens, the structures that form when you increase the attractive interactions between the particles. So the thing that we've already discussed is what happens when the attractive interaction is very large compared to kT, and the volume fraction is in fact very small. That's the case of colloidal aggregation. So here, in this small region up here, the volume fraction is low and the attraction is very, very large. Then you get irreversible aggregation, and as I said, if you can avoid any other effects like sedimentation or flow or anything like that, and you have the time to wait for diffusion to occur, the size grows linearly in time, but it takes time for this to happen, for the sizes to get large enough. But if you can wait, you will ultimately form a gel, a continuous network. And there's a lot known about these gels. Again, I don't have time to discuss them, but you can measure both with optical techniques. You can measure the fluctuations of the gel, and using mechanical measurements, you can measure the strength of the gel. You can measure the fact that they're elastic, and you can actually predict the elastic constant of the gel quite precisely. If you consider other cases, if you imagine this region of intermediate volume fractions where there's some attraction but not too much attraction, then you can still form a gel if the attraction gets large enough. And so there's some phase boundary here between states that are equilibrium. They're still sticking together, but they're not sticking together enough that they form a complete network. However, if the volume fraction goes up or the attraction goes up, at some point you get them to stick together in some way that forms a continuous structure that remains stationary in time. So you get a jammed or a non-equilibrium state that forms a solid. And I'm going to come back and look at this in a few minutes. Finally, if you go to very large volume fractions, in fact, if you go to very large volume fractions and have no interactions whatsoever, then you can get a system where the crowding of the particles actually traps them and they become a colloidal glass. And I'm going to discuss that for a few minutes. But this colloidal glass extends also to weak attractions. What's interesting here is if you notice, let me use my pointer. Sorry, this is the colloidal glass. If you notice the shape of the phase boundary, the phase boundary between the non-equilibrium glass-like state, which is here, and the equilibrium fluid-like state actually is shifting over towards higher volume fractions. So it actually becomes more fluid at higher volume fractions if you introduce a weak attraction. And the physical reason for this is that the particles are crowded, and I'm going to discuss the crowding of these particles. That's why they are forming a glass. They're getting so crowded that they can't relax. But if you have some transient attractions that pull some of the particles together. And so locally you might have a little cluster of particles that are stuck together. That means that around here the volume fraction will be a little bit larger, or a little bit lower, so there's more free space, and that lets the particles that are not stuck together actually move. And so this actually, the effect of this is to have a small region where there's more mobility even at higher volume fractions. So to measure the mechanical properties, we use rheology. I touched briefly on this the last time. Essentially, you put a deformation on the sample. Say you apply a deformation at some known strain and some known strain rate. You put an oscillatory deformation at some frequency omega, and you measure the stress in response to that deformation. So here you might move this plate some known rate and amplitude, and here you'd measure the stress, and you measure the imaginary stress, that is, or the complex stress. You measure the stress that, and you convolve it into the stress that's in phase with the drive and the stress that's out of phase with the drive. The component that's in phase with the drive is the elastic component of the elastic modulus. The component that is out of phase, that lags by 90 degrees, that gives you the viscous component. And so if you just look at hard spheres along that line where there's no interaction, you see this behavior for the elastic and viscous component as a function of volume fraction. Notice the volume fraction is changing from 50 to 56%. You see that the elastic component becomes larger and larger. It increases by well over an order of magnitude, and it goes from something that's increasing with frequency to something that's quite flat with frequency. And if you look at the highest volume fraction, you see that over the range of frequencies that are most accessible, say from a tenth to 10 hertz, that's the sort of time scales that you're most sensitive to yourself. Notice that the elastic constant is actually quite a bit larger than the viscous component, and is essentially, not completely, but essentially becoming independent of frequency. That's the signature of a solid-like behavior. At long times, you still get this relaxation, and of course, at short times, you become dominated again by the fact that these are in a fluid. So interestingly here, you have a system where there is no interaction between the particles. These are hard spheres. There's no interactions. The only interaction that can be important here is entropic, just free volume. Nevertheless, you get something that's forming an elastic material. It's a solid material just through entropic effects. And that's exactly what was predicted by the early computer simulations. You can understand that physically by looking at this diagram here. Here are the particles. They're undergoing free diffusion. And imagine that I apply a small strain in this direction, shown by moving the plates. The particles then move in this direction. If I do it rapidly enough, the particles move in this direction and have a new configuration. They will begin to relax back to their equilibrium configuration, but this will take time. In fact, the amount of time it will take will increase significantly with a volume fraction, simply because they're becoming more and more crowded. They have less and less space, and therefore they can't really relax with respect to their neighbor without having other particles surrounding them also relax. But if they have the time to relax, then they will go back to their elastic, to their equilibrium configuration, and that just takes quite a bit of time. If, on the other hand, you move the plate back in the opposite direction in a time scale short compared to that relaxation time, then during the time the plates have been displaced, the particles have been out of their equilibrium configuration. If they're out of their equilibrium configuration, they are automatically in a higher energy configuration. And you're not allowing that to relax before you move into another new non-equilibrium configuration by moving this to the same amount to the other side. So during the time that the plates are displaced, the particles are in a higher energy state, and it's just due to entropic energy, because that's the only energies that are important. And as a result, you're storing energy in the system. If you store energy in the system, that's what you do in a spring. So the response of this will be in phase. It will be an elastic response. You'll actually have a solid, and that solid is due simply to the fact that you're distorting the equilibrium configuration of the particles. Now, if we go, before I do this, if I go back and I look here at these very crowded situations, we can understand something about the nature of the relaxation of the crowded situations by using confocal microscopy and actually watching the particles relax. So we do that by taking these three-dimensional images. I showed you last time how we take three-dimensional images with confocal microscopy. And then for every particle in the system, we do essentially, we identify the nearest neighbors by doing what's called a Delaunay triangulation. That is, we look at all the nearest neighbors, we define nearest neighbors from the using a pair correlation function, and say going out to the first minimum or slightly beyond the first minimum of the pair correlation function. That would be a spacing corresponding to roughly like this. And then just drawing arrows to all of the particles that come in within some distance, some relative distance compared to that. So here, this red particle, we're showing all the nearest neighbors. So you identify both the particle and its nearest neighbors, and then you watch how the particle moves as a function of time, and you do that by tracking each and every particle and calculating the mean square displacement of from the data. So here's the mean square displacement shown here. This is the mean square displacement as a function of lag time, or as a function of time delay. And this is collected over many different sets of data, all using taken with a confocal microscope, where each particle is tracked. So you're following the behavior, the motion of each particle. And you look at the data and you see there are three general regimes. In the intermediate frequencies, there is some fluctuations, but the fluctuations barely change with time. So there are fluctuations in the position, but the amplitude of those fluctuations don't really change. The step size doesn't change as a function of lag time. At early times, you see that it changes, it increases from a very low value, and at late times, it begins to change again. This is exactly the behavior that you expect on a molecular scale for a glass-like material. At very short times, you can think physically, at very short times, the particle doesn't know that it has neighbors. It's undergoing diffusive motion inside a cage. In fact, I show that in the next slide. Here, I show that in the next slide. If I look at this particle, at very, very short times, it has very little time for diffusion, has very little time for motion, and but so it doesn't go very far. So it diffuses, but it diffuses in the cage. It diffuses around in the cage, and eventually it reaches. So it's diffusing to the boundary of the cages. It reaches around to the boundary of the cages, and at that point, so at early times it's reaching the cage. At later times, it's reached the boundary of the cage. So it doesn't diffuse until ultimately the cage breaks, and it jumps out of the cage. That's shown here in this insert. You're diffusing here, you're trapped in the cage, and ultimately the particles move away and it jumps to here to a new position. And this is called cage breaking, and this is called cage trapping. Okay, let me now, I'm going to continue on and discuss this, but let me take a little bit of a break and answer some questions. So Ming has a question in slide 21. What is the difference between alpha relaxation here and glass transition of a polymer glass? It's essentially the same thing. This is going to be the alpha relaxation is the long time relaxation, and this is the long time relaxation. And I'm going to actually describe what that means from a physical point of view just in the next slide. Is the time scale the same? The time scale here is set by the characteristic diffusion time of the colloidal particle. So it's all set by the size of the colloidal particle and the viscosity of the background fluid. So it's very different than the case of a polymer. But the physics is more or less the same. Of course, in the case of a polymer, you can do the same thing with these. If you would just join these together into a freely jointed chain, you could make a polymer. The relaxation mechanism is different than in hard spheres. And in fact, we'll look at the relaxation mechanism right now in the hard spheres. Any other questions? Okay, let's continue. Here are some examples measured with a confocal microscope showing cage breaking. These are trajectories of individual particles. The black to gray is the evolution of the time, so that shows how the time evolves. And we're just plotting the trajectories. This is, of course, a two-dimensional plot of a three-dimensional motion, so everything's projected into a plane. And you see that for some period of time the particles are trapped, then they jump out of the track, they're trapped, they relax compared to the neighbors, and again they're trapped. And this kind of motion is exactly what's reflected in this behavior of the mean square displacement. At early times, they're trapped in a cage. At some point, they jump out of the cage, and then they start moving. Now, although it looks like when they jump out of the cage, they start moving again, the motion here, of course, is relative to the short time. So you're essentially jumping back into this regime. If you watch what happens out here, this is comparing the motion here compared to something over here. So the step size is much larger. And if you go to very long times, again, this is logarithmic, so going another decade, just moving a decade down here is a time 10 times as long, then you start seeing many of these jumps. It'll jump here, jump here, jump here, jump here. It's essentially undergoing a random walk again, but now this is a random walk of these stuck regions. And so the motion again increases roughly linearly, but now you're seeing the motion, you're obscuring the cage trapping, and you're looking at the jumps between cages and its consequences for the motion. So we can further analyze the behavior. Remember, I showed you when I first discussed what you can do with tracking with confocal microscopy. You can also look at the step size distribution. And remember also that I looked at the step size distribution for diffusing particles, and that was Gaussian. If you plot the step size distribution of the Van Hove correlation function here on this inflection point, you see that at the larger steps here, or the smaller steps here are in fact Gaussian distributed, but there are big tails where there's much larger steps. This is exactly reflecting what we saw in the trajectories. That is, most of the steps were small because you were trapped in the cage, and so the dominant number of steps are in here. But every once in a while you take a very large step, and so there's some very large steps, and they're much larger than you would expect if you had simply diffusive motion. So you have this very non-Gaussian contribution. You can parameterize this by the non-Gaussian parameter, which is just this distribution, or this ratio of distributions, the fourth moment compared to 3 times the square of the second moment minus 1. And this is just a measure of how non-Gaussian the behavior is. And if you plot this non-Gaussian parameter as a function of time, here's the mean square displacement, here's the non-Gaussian parameter, you see that it exhibits, for all the different volume fractions, it exhibits a peak corresponding roughly to the inflection point. Not exactly, but roughly to the inflection point. And this peak is fairly large if you look at it. So now you can define something. You can define 2 different parameters. You can define a characteristic length, you can define this length by the length where you get this larger scale motion. So after some of these jumps, there's some length scale that you see this this large scale motion, and this occurs. There's a peak in the non-Gaussian parameter occurs at some characteristic time. If I go back here, you see that there's a characteristic time. So I can describe in this case both a length scale and a time scale where you see this onset of really non-Gaussian behavior. And these characteristic length and time scales are some transition point between Gaussian and non-Gaussian behavior. And this is where you're essentially reflecting the fact that the relaxation, the motion of the particles, is no longer single particle-like, but there's some collective effect. And the contribution of this becomes larger and larger as the volume fraction increases. So if you go, let me get back here, if you go to fairly large volume fractions, notice that this is decreasing around 56%. Here you have a very, very strongly non-Gaussian behavior. You have something where the mean square displacement, I'm not showing the full range of it, but here the mean square displacement barely increases at all with time, and here it gets very, very slow. You can it increases with time, but it's slowed down substantially from what it was here. So at any given time, the amount of motion is much, much less. You can understand this by looking at the individual particles. And there's a movie here, which, Mayun, if you could play the movie, this is a movie showing just the red particles are those particles that are moving. You wait a characteristic time and you watch them move, and you just plot those particles that move. Now, I hope on your computers it's playing better than mine. It's now starting to play on my computer. It depends on your connection. But you see what happens is that there are very strongly spatially correlated regions where there's motion. And the bar on the left is the time increasing uniformly. The bar on the right shows the number of particles that moved in the last characteristic time. And you'll see that that fluctuates madly. At sometimes a lot of particles move, and if you look in the plot, you see there's a lot of red particles moving. Other times, very few particles move. But the important thing is that when particles move, they don't move locally by themselves, but rather there's these very large correlated regions of particles that move. You can understand that physically by just recognizing that the particles are crowded. They're all pushed together. So if things move, if one particle has a fluctuation that allows it to move, it essentially moves, and there's a free space behind it where it's moved from. And so another particle can move into that space. And that's why you get these very strong spatial correlations of the particles. Okay, you can stop the movie, Mayun. Thank you. So if we go back to the non-Gaussian parameter and now go to even higher volume fractions, here before we looked up to about 56, at volume fractions of 60 and 61, now you no longer really see a well-defined peak in the non-Gaussian parameter, and in fact you see that there's virtually no relaxation anymore in the particles. There's some, and you can define that by saying, well, let me look at the, say, 5 or a couple % of the particles that move the most, but let's plot where they are. And so could you please play this movie, Mayon? Now again, the red particles are those particles that have moved the largest amount. I think we took about the 5% particles that move the largest amount. And you see that they're very, very randomly distributed in space. You don't see this strong spatial correlation. The relaxations can occur anywhere. And that's because they're so concentrated that you really can't get this large-scale relaxation. And in fact, if you go back and turn the movie off now, thank you, Mayun. If you go back and you look at the behavior, you see that the mean square displacement, the mean square displacement is essentially constant in time, and there's this very, very weak upturn at the very longest times, and even this is somewhat suspect because you're getting to the length of time, the delay time here. Notice the delay time is 10 to the 4 seconds. So this is looking at delay times of 20 minutes, and or no, even longer. No, sorry. Yeah, yes, some number of hours, I believe. So you're looking at very, very long delay times here. And so in any given experiment, you're not really taking very many independent measures. So you have to view this with a bit of a distrust. But the important thing is that there's very little relaxation, very little motion of the particles. So you can look at, remember I showed you these fluctuations in the number of particles that were undergoing relaxation. When they were strongly correlated at 56%, if you plot the number of particles or the percent of particles undergoing fluctuations as a function of time, you see these large fluctuations in the number that are undergoing. It can be 6%, it can be down at 2%. And the characteristic time of these fluctuations corresponds exactly to the relaxation time of the system. You can see similar correlations here, but in this case the correlations, the number of particles are not so strongly spatially correlated, and so on average there's the same number of particles undergoing this relaxation as a function at any given time as it was before. So you can look at the properties of these connected regions. The connected regions themselves form these clusters. That's shown here. So these are the dynamically collective regions. These are the particles that are undergoing some relaxation at any given time. And you can see that they're what's called structurally heterogeneous. That is, you see this region that's undergoing relaxation, whereas nothing else is, and you can plot what the size of the region is just by the number of particles that are contributing as a function of the radius of gyration. And sure enough, you see a fractal-like behavior, and the fractal dimension is about 2. That means they're very tenuous, but not that tenuous. And you can plot the distribution function of these things. There's a lot more that you can do with the statistics, but perhaps the most important is this. That is, that if you plot what the average size of these clusters is as a function of volume fraction, remember volume fraction, you're increasing the volume fraction, you're making it more and more crowded, you see that the size increases. It increases rather dramatically. We don't have a huge amount of data, but the general trend remains the same. And it increases rather dramatically up to some point, and then boom, it stops increasing anymore, and in fact decreases. And so here you get this large correlated region, and now you get no relaxation at all, or just individual particle relaxation. And this boundary is essentially the glass transition. You're driving the system, you're making it so crowded that it's becoming a colloidal glass. And that's exactly the nature of a colloidal glass. But what you can see is the origin of this is that you're making because it's becoming so crowded, one particle cannot relax completely with respect to its neighbors without undergoing motion of several other of its neighbors. And that's what leads to these strong correlations in the regions that relax. And of course, the region that things slow down when you become a glass is because it becomes more and more crowded, and the range of these relaxations becomes larger and larger. So the time length it takes, or the time scale it takes for these relaxations at these very high length scales increases and begins to diverge. And there's still some debate. I don't think the data here are good enough to tell you whether this is a true divergence or just an increase. But this is what defines the colloidal glass transition. So we can go back to this picture here that I showed you before of the transition between these equilibrium states and these non-equilibrium states. I've talked now about this colloidal glass. We've talked about aggregation. Now let's consider the much more widely applicable and important condition experimentally and technologically. That is where the system becomes fairly crowded with a fairly weak interaction, and then over a fairly wide range of volume fractions you have this weak interaction, and in order to get from a state that's purely equilibrium to something that's essentially jammed into a solid state, you have to increase either the interaction energy, make them more attractive, or you have to increase the volume fraction. It's some trade-off between these two things. And we can try to understand that now by looking at the nature of this trade-off and the nature of the behavior of the particles. So let's look at this intermediate regime. And here are some images that are taken of one particular colloidal system, where what's happening here is you're changing, in this point, you're changing the interaction energy. You're going from a system where the interaction energy is very low to a system where it becomes much higher. And these are colloidal carbon black particles, or carbon black particles. And they're sticky, so they go from where, if you prevent any stickiness, they go from the case where they're fully dispersed to the more normal case where they're starting to form these large clusters. And in this regime, just by looking at it, I can tell you that it's more or less a solid by now, that you've gone into this jammed state, into this non-equilibrium state. So you've gone in this direction, and you've gone from the case where they're an equilibrium fluid to a gel, a solid gel. Here they're an equilibrium fluid, and here they become a solid gel. If you shear the particles, that is, you put a shear rate on the particles, you also can go from, in the case of no shear, where you form this network, you can break them up and form a system like this gel just by shearing the particles. So we can understand something like that. We can look at the behavior as a function of volume fraction, and here I'm plotting just what images look like at very low volume fractions. You get the dispersed phase. As you increase the volume fraction, you go into this gel phase. At very high volume fraction, notice it's just 4% by weight. If I convert that to, I'll show you how you convert that to volume. In fact, let me just go to where it's converted to volume here. It's converted to volume fraction. If you go to increased volume fraction here, it goes to much larger. It gets so large, in fact, it gets so dense because it becomes very sticky. Just to go over what I skipped over, if you want to look at what the real volume fraction, here what you're really measuring is what the image looks like, and you're measuring the weight fraction. That's what you can mix. If you want to measure the effective volume fraction, you have to convert from weight fraction to volume fraction. You can do that purely mechanically by measuring the viscosity as a function of shear stress, of shear rate. And you see that as the rate increases, the system shear thins. The way to understand this is that you have some attractive interaction between the particles. They get larger. They form fractal objects. The fact that they're fractal objects means that they occupy much larger amounts of space. Eventually, they occupy so much space that they become very solid-like. However, the interaction is relatively weak, and so as you increase the shear rate, you increase the stress on the system, you actually decrease the effective interaction energy. So you get this very, very strong shear thinning. And if you shear at high enough rates, you get this system to be completely unaggregated. You get it to be dispersed again. And now what you can do is you can look at the viscosity in this fully dispersed phase. And if you look at that here, this is a high shear rates. Then you see that they asymptotically approach a value where there's now a very weak dependence on viscosity of the weight fraction. But there is a dependence. And this dependence you can just use. You can use the theory due to Einstein, or the theory due to Batch, or any theory that says how the viscosity changes with volume fraction. It changes relatively slowly, but it is noticeable. And you can use that then as a conversion factor to go from weight fraction into volume fraction. That's shown here. So that's how you measure the volume fraction of the system. Now we can look at the rheology of the system. So what I'm plotting here are the elastic and loss moduli for gels formed that are very low volume fractions. Notice that the dominant term, these triangles, is the loss modulus, and there's an elastic modulus only at the somewhat larger volume fraction. At the very weak volume, very low volume fractions, there's barely an elastic modulus whatsoever. However, if you increase the volume fraction, now we've gone from 0.04% to 0.06% to 7%, or sorry, 0.06, so 6%, 8%, or 10%, 15%, and now you see qualitatively different behavior. This is closer to what you see at the low volume fractions, where you have predominantly the viscous contribution, and here's the elastic contribution, to at lower strain rates. This is done with oscillatory measurements. At lower frequencies, you see that you become increasingly solid-like, and as the volume fraction increases, just reflecting the fact that this looks much more solid-like than this. And so the modulus is increasing, and in this case it's increasing by several orders of magnitude, maybe 3 orders of magnitude, because here it's 1 and here it's 10 to the minus 2. But what's interesting about these data is you can take them, so I can take the middle data and I can plot it, it's a log-log plot, I can plot it on top of the data on the right, and then I can shift the data until they completely overlap. So I can scale the middle data onto the data on the on the left. And I can do the same thing with the data on the right. I can scale it so you get things scaled. And this is in fact how I got this scaling curve that I showed you at the very beginning of this set of lectures. This is the behavior of a very traditional soft material. At low frequencies, you get a predominance of the elastic modulus, and at high frequencies, you get the predominance of the loss modulus, and the loss modulus is always, at the lower frequencies, is always some small fraction of the storage modulus, of the elastic modulus. So it's viscous, but its viscosity is much less than its elasticity. Moreover, somewhat surprisingly, there's this flat region of the viscous component. And the thing is that when you make measurements like this, you rarely see a viscous response, which should normally depend on frequency. You rarely see it be independent of frequency the way it is here. You can understand this scaling behavior that I showed you here. You can understand the scaling behavior by just understanding the very simplest kind of behavior of this network. And I can point that out by looking at this network here. You have, in this case, about 6% of the sample by volume is made up of this network. And that solid network is the only thing that can contribute elasticity. That's what leads to elasticity. However, this dominant component is still the fluid in the background, and that has something that looks like a viscosity. If you go to the highest volume fraction, here it's still only 15%. So only 15%. You can't see through it because you're looking through a three-dimensional object, but only 15% of the material is actually solid-like. It's still predominantly liquid-like. So now you can go and understand from a simple perspective where this comes from. Imagine that you have a contribution due to the liquid, and when you plot it as something that's a viscous fluid, what that looks like is the loss modulus, shown in blue, will increase linearly in frequency. It's just reflecting the standard viscosity of a Newtonian fluid. Similarly, there is a solid component, and that anything that's solid is independent of frequency, but its magnitude depends very strongly on the concentration. So at different concentrations, you'll have the loss modulus, the viscous contribution, is always just going to be the same. And since you're predominantly made up of the fluid, and the fraction of fluid doesn't really change very much, it might change from 95% to 85%. It's really not a big change. So I just assume that this is more or less independent of time. But the elastic modulus changes rather dramatically. But if you want to shift one set of data onto the other, all you have to do is look for the crossover. So for any given, like for these middle data, you might say that the response is predominantly elastic here, predominantly loss-like here, so it's predominantly something that looks like this. And I can shift, I get the same behavior at different volume fractions, just shift it over. I can shift any set of data onto another just by shifting this crossover point along the viscous component. And that's shifting it along the viscosity, or shifting it linearly on this plot. That is, shifting the amplitude by the same amount as the frequency. So I can test this by plotting the shift factor that scales the data together for the y-axis, for the amplitude of the moduli, as a function. I plot that as a function of the shift factor for the frequency. And if I do that, I do indeed see this linear behavior. And that sort of confirms that basic model. That is, I plot the scaling factor for the y-axis against the scaling factor of the x-axis, normalized by the bare viscosity, because the viscosity itself of the background fluid might change. I normalize by that, and I get this very nice linear behavior. Now I can plot, because I can make these kinds of measurements, I can look, because I can scale them together, because I can do the scaling factor, if I see a very weak sample, I can measure it up at this other regime where it's predominantly fluid-like, but by shifting it, by scaling it, I can measure the weak contribution of the elasticity, because I know where this crossover point is. I can measure it even if I can't actually access those frequencies. It's just happening at very low frequencies. So I can plot the zero frequency value of the elastic modulus as a function of volume fraction, and similarly I can plot the characteristic viscosity, say at some frequency, as a function of volume fraction, and I get this behavior where at some characteristic value of volume fraction I see a divergence of the elastic contribution, of the viscous contribution. It diverges as the volume fraction goes up, and I see this kind of diverging fall off of the elastic component. That is, the elastic component is fairly large, but as I approach some characteristic value here, the elastic component gets lower and lower and lower. And anytime I see something like this, I'm plotting this because I want to explore large ranges in elasticity. I'm plotting this, the logarithm of the elastic component. This is the elastic component where it's flat, or the crossover value, as a function of the volume fraction. So it's log linear. Anytime I see this with some kind of offset like this, the natural way to plot it is in a scaling plot, and that's shown here, where what I've done is I've taken the elastic modulus. I can subtract off some some low value, but it's so small that I don't have to, and I'm plotting that as a function of volume fraction, but the distance of the volume fraction from this characteristic value. So this is the measure of the volume fraction. So this is how much excess volume fraction I have compared to the volume fraction that's required for the sample to begin to become solid-like. And I see that I have this scaling behavior. The elastic modulus is a function of phi minus phi c. I can identify what this characteristic is, and I see I get this scaling behavior, both in the elasticity and in the viscosity. So the elasticity is increasing dramatically. It's increasing as a power law compared to the distance you are from this critical point, and the viscosity is decreasing, or is increasing also as you go to that critical point. This allows me to define very precisely where that critical point is. So I can look a little bit farther. One of the things that you can do is change the interaction energy. You can do that by just adding essentially a surfactant that absorbs on the surface of this. This is a technologically very important thing. You add dispersants, but all it is a surfactant that sticks to the surface. So you add the surfactant and you redo the measurements. Here you recalculate the volume fractions, you redo the measurements, and again you get data that follow the same shape. Again, the data scale together and follow the same shape. So what I'm doing now is these light points shown here are the data from before, and I'm just taking the new data where what I've varied, I fixed the volume fraction at 15%, and I'm varying just the concentration of the dispersant, and I still get all the data to scale together like this. And again, you get this scaling behavior, this critical behavior, where now it's a function of what we calculate. We can convert the concentration of the surfactant into an interaction energy, and you do that by taking a model for the surfactant of a brush, a polymer brush, and taking the theory for polymer brushes, what the interaction between the particles are for polymer brushes. When you do that, you get this kind of behavior, and the take-home message of this is that you can define a characteristic value where either of energy or volume fraction, where you cross over from fluid-like behavior to solid-like behavior. And so that's shown here. There is some characteristic value, and I've shown cuts to identify that. I've shown cuts along a constant interaction energy where I change the volume fraction, or a constant volume fraction where I change the interaction energy. And there is a well-defined point shown by this scaling behavior where you see this crossover. So this line is absolutely well-defined. And so, interestingly now, what I've showed you is that you can change either the volume fraction or the interaction energy. You also can change the shear. So if you shear the sample, you go from this aggregated state to this more displaced shape. So you can do the same behavior with shear. You can see exactly the same type of behavior. Here you can see here we're plotting the viscosity as a function of shear rate. From this we can calculate the stress as a function of shear rate, and you see you have this characteristic behavior that at low shear rates this is increasing linearly. So the sample, the stress is becoming independent of shear rate. Anytime you have a sample that the stress is independent of shear rate, it's basically behaving like a solid. So this is behaving like a solid at low shear rates and going to a fluid at higher shear rates. So you're essentially shear melting the sample. You're melting the sample, you're changing it from a solid to a fluid by increasing the shear rate. And this behavior here, you can do exactly what we did before. You can take any two sets of data, scale them together so they come into one universal plot. Here's a couple of examples of this. And this is the kind of scaling behavior you get. Sorry for the symbols here, but these are just shear rates. And you see that the stress or the viscosity scales for all the data scaled together, just like you got the same scaling before. And so, again, you can use that scaling behavior to define some boundary between the fluid and the solid solid-like behavior. This is as a function of volume fraction or as a function of interaction energy. You see the same kind of boundary behavior. And so you can take all of this, the volume fraction, interaction energy, and the shear rate, and you can make them into a three-dimensional plot. I'll just skip over these. This is details which you can read later, but you can make them into a three-dimensional plot. This is now plotting the stress, the inverse of the volume fraction, so increasing volume fraction moves inwards, and the inverse of the interaction energy, so increasing interaction energies moves down. And that means in this lower inner quadrant, you have a system that becomes solid. So this is actually exactly like the jamming behavior. This is a proposal by Andrew Liu and Sid Nagel about how glasses behave. They were thinking about more traditional materials where there's a repulsive interaction between molecules, but in fact, if you look carefully at their proposal, you would also see the same behavior in attractive interactions. And this is just an example of an attractive interaction leading to a system that is jammed, is solid-like non-equilibrium behavior in this lower quadrant. Now, the fact that it's inside compared to the way I plotted it before is just that I'm plotting the inverse. I'm plotting 1 over the volume fraction here, the shear stress, which I wasn't showing before, and 1 over the energy. So I'm just plotting the inverse of that. It's exactly what I showed before, except before I showed it in more experimental parameters. This is in a more theoretical parameter. So this is an example of the of jamming. This is, in fact, one of the very earliest examples of jamming behavior in general. Let's see. Now I'm going to go back to this phase behavior, and this is what I showed you before, this U versus phi phase behavior. But in fact, if I think about interaction energies, or interactions between particles, I can think of another parameter, and that's the range of the parameter. And the range of the interaction, you have an attractive interaction, but there can be a different range to it. And that is very often the case in colloidal systems. You can easily induce attraction. I won't describe how, but it's a very simple thing to do, where you induce an attraction that has some range to it. Physically, the way you do this is you use a depletion attraction where you add small particles or small polymers to these larger colloidal particles, and the effective behavior of the small particles is to put an osmotic pressure on the large particles. Let me see, do I have it? I may even be able to draw this. Let's see. No, I can't. Okay. Oh, here. Now I can. Let me draw the react. Where did it go? I'm going to try and draw. Depletion interaction. I have one particle here, another particle here. These are supposed to be spheres, and I have lots of small particles in between them. So many small particles, and now, okay. Somehow, here we go. Somehow now you can see that the small particles exert an osmotic pressure on the large particles. If the two large particles come close enough together, then the small particles cannot fit between them. If they can't fit between them, they can't exert a pressure that pushes them apart. So there's a pressure that pushes them together, but nothing that pushes them apart. And that's the depletion of the small particles from between the large particles. In that case, there's essentially a pressure that pushes the two particles together and creates an attractive interaction. And that's the depletion interaction. The size of the small particles determines the range of that interaction. So now let me look what happens. And so now imagine what can happen is, we have this same interaction. This is this gel line, this phase transition, but there is actually, whenever you have some attractive interaction, whenever you have that, there's a possibility of having some spinodal decomposition. Typically, for a short-range interaction, this spinodal decomposition is hidden. You form a solid structure before you can actually see the spinodal decomposition. However, if you increase the range of the interaction, you shift this spinodal line down towards lower interaction energies, basically because you're making the range of the interaction so large. And so if you go to very low interactions, you can actually see spinodal decomposition, or it's predicted that you can see spinodal decomposition even before you see this non-equilibrium state. So this is where it's purely equilibrium, and you get some phase separation between a colloid poor region and the colloid rich region. And you actually can see that. That's shown, it's shown in the next slide. In order to take these data, you have to get rid of buoyancy effects, and no matter how well you index match it, if you really want to watch this properly, you can't do it on Earth, but you can do it in microgravity. So these are experiments taken in microgravity. And so here's an experiment where this is a sample cell. This is about pi centimeters across, about 3.1 centimeters across. The bright regions are a colloidal suspension, and what I'm going to do is I'm going to start, this has been shaken up so everything's uniform, and then I'm just going to stop shaking it, and I'm going to watch over the course of essentially 35 hours, I'm going to watch the effect of this long-range attractive interaction. And Mayun, if we could play the movie now. This is a movie. And as you watch it in time, this is taking images, snapshots over the course of 35 hours. You see not much happens, and then you see spinodal decomposition. You see phase separation begin to happen, and the regions of bright regions are colloid rich. Okay, that's enough. Thank you, Mayon. It's just playing again. You see this happening again. But if we can turn the movie off, thank you. Here are some images over the course of time. This image is near the end of where the movie was, and then eventually, if you wait long enough, and this is if you wait several days, you see complete phase separation. So here's completely colloid rich, here's colloid poor, and if you in fact look carefully, you see along the boundaries of the sample, you see that there's colloid rich region. So the colloids actually wet the sides of the sample. And you can plot from measurements like this, either from doing scattering measurements, from doing Fourier transforms of the images, or just by measuring this with a ruler. You can measure the characteristic length of this. From that, you can calculate the characteristic wave vector that you see. These are measurements made with light scattering. These are measurements made with image analysis. And you see that as a function of time, this is scaled to the diffusion time of the particles, you see that you get this very characteristic behavior, and there's a calculation for phase separation for spinodal decomposition over long times by Furukawa that exactly agrees with this. But in this case, unlike the normal case of spinodal decomposition, which is done at a molecular scale, this is done at a colloidal scale, where the initial particles or the objects that are spinodal decomposing are much, much larger. They're colloidal particles rather than molecules. So this is just consistent with exactly what you would predict. But now what happens if you go back to a short-range interaction where this is hidden and you can see the gel-like behavior? How can we understand that? How can we describe that? So there's a question in slide 63, which was this phase separation, I believe. Yeah, what polymer did we use? I think it was, I believe it was polystyrene, but I'd have to check. I don't really remember. It's some polymer that is an inert random coil polymer in the solvent that was made to index match the colloids. And I think it was polystyrene, but I'd have to check what it was. Okay, what I'd like to do is look at the what's the interaction. It's just excluded volume. There's no interaction whatsoever. The polymers are very small. They were about in that case, they were about 20 or 25% of the size of the radius, so they're fairly large range interaction. And it's purely an excluded volume effect, both the interaction between the particles and the interaction between the polymer and the particles. Yes, it's just depletion interaction. That's the only thing that's happening. Okay, so if we go back to this, what I'd like to do is look at what happens here. How can we understand if there's any relationship between spinodal interaction, spinodal decomposition, and let me just skip ahead. These are just a few measurements. Let me skip ahead to slide 69, Mayun. This is a movie. This is what happens. This is the way the particles look in the absence of any polymer. If we play the movie, you can see if it plays properly on your screen, they're diffusing around. They're just acting as hard spheres. They're coming close to each other. They're moving apart from each other. And that's enough. Thank you, Mayun. If we can go to the next slide. The next slide is also a movie, but here's a movie where we've added some polymer. So this is looking at a very weak interaction. And as these play, you can see that now the particles come together. This is depletion interaction in action. You see the particles come together and they're breaking apart. They come together and they're breaking apart. Here we're using a very, very small polymer. The polymer is about I think about 8% or 5% of the radius of gyration of the polymer, 5% of the radius of gyration of the particles, and it's inducing a very weak depletion attraction between the particles. Thank you, Mayun, for the movie. We can take that off now. But what you can do is you can, in that case, you can take snapshots and you can measure the distribution of the clusters. You saw that the particles would stick together. The clusters wouldn't interact constantly. They come together and they break apart. So you take snapshots, and as a function of polymer concentration, shown here as polymer concentration, you can plot the distribution of the clusters. Most of them have cluster size of 1, and there's some that stick together, and the distribution looks like this. And the point of doing this is that you can compare this to simulations, and people like Francesco Scartino does very simple simulations that predict what the distribution is as a function of effective temperature, of interaction energy. They fix the interaction energy to change the temperature. What you're doing is you're measuring it as a function of interaction energy over temperature. So this gives you a way of converting from polymer concentration to an actual temperature just by looking at these simulations. And what's interesting about this is that they do simulations for a variety of different interactions. It doesn't really matter what the shape of the interaction is. It only matters what the range, what the amplitude, the depth of the interaction. So you can take any interaction shape that you want as long as it's fairly short ranged. So this is a way of very precisely determining a temperature, a thermodynamic temperature, which you can't determine. The actual temperature doesn't matter. It's really the ratio of the interaction energy, which is determined by this depletion interaction and hence by the concentration of the polymer. It's a way of converting that into a true thermodynamic temperature. Okay, so this is just showing that it doesn't matter. This is a calculation for different shapes of the interaction. You see that it really is independent of shape of interaction. And so now you can look at the behavior as a function of polymer concentration, and you can identify that point where it gels. And this is a movie that shows a gel, a confocal image of the gel. And, can you play this movie, please, Mayun? And this is just going to slowly rotate. It's not playing yet on my computer. Okay, it's not really, the bandwidth is not so good on my computer, but this rotates and just rotates around. Okay, that's enough. There we go. Now it's playing. You can see that this is a solid network. This is taken, this movie is taken for a concentration of polymer right here, right at the middle, where the gel is just formed. And this gel is permanent. If you watch it over time, it continues. Oh, this is good. It continues. Okay, thank you, Mayun. So you can look at the structure of the gel. This is a movie as well, but I think you can play it. I hope you can. Okay, now we can play it. And you'll see that there's fluctuations in the structure, but it stays. The gel stays as a connected network. It fluctuates in space, but it remains. Over time, it remains constant in time. Thank you, Mayun. Maybe we just can move on to the next slide. And so now what we can do is we can plot, as a function of concentration of polymer, we can plot the actual energy of interaction. And here we're plotting the inverse of the energy of the interaction. And you see that it's basically linear. I can draw a line through that. It's linear. And what you can do is you can compare this with calculations for where you get, experimentally, where you get, this is a measure. This is the value of the gel, where very precisely we can measure at this value you get the gel. At these lower values, it's fluid-like, and beyond this point, it's gel-like. You can compare that to both analytic and simulation calculations of where you get the binodal boundary, where you expect to see the beginning of the phase separation due to binodal. And what you see is exactly where it gels is exactly where the binodal point comes. And this is the same for all different types of ranges of interaction, for all different types of polymers, different ranges. You always see that gelation occurs exactly where spinodal decomposition occurs. So you cannot get gelation unless you get spinodal decomposition. They occur at exactly the same point. As soon as you cross into the spinodal region, then you get gelation. So now we can understand that. First of all, we can understand the implications of that, and that is shown, I think, well, okay, it's shown in these graphs. That is, if you plot the structure factor as a function of energy or as a function of time, you get the behavior exactly like, you get a structure factor exactly similar to what you expect for spinodal decomposition. It's shown most clearly here, where there's a peak that grows in time and moves out in time. And this is exactly the type of behavior that you see in spinodal decomposition. And in fact, if you watch it as a function of time, it's summarized here, and I'll ask Mayun in a second to play this. What I'd like you to do is watch the formation of the structure. The gel is the red, the free particles are the blue, and this is a cut through it, and this is the structure factor, the calculated structure factor over time. So please, Mayun, can you play this movie? So now, I'm not sure how it will play on my computer. It's fairly slow, but now you can see it forms, and you can see that the gel forms, and the structure factor goes up and exhibits this characteristic behavior of structure factor of spinodal decomposition. Well, we can play it one more time, but I think that's clear enough, Mayun, and maybe just in the interest of time, we could just continue. So what this says, thank you, Mayun. What this says is that what you have is essentially a spinodal decomposition. Wherever gelation occurs is exactly spinodal decomposition. That's shown here, but it's maybe shown a little bit more clearly. Well, okay, it's shown here reasonably well. This, when you move up, what you're doing when you turn on this interaction, you go from no interaction to an attractive interaction. You're crossing this spinodal line, and the result is you undergo spinodal decomposition, and that's what leads to the gelation. You get this region where there's very poor in polymer, there's almost no, very poor in colloids, almost no colloids, there are very, very few monomers, and the second region where it's very concentrated. And in fact, if you measure the concentration in this very concentrated region here, if you measure the concentration, it is exactly the concentration. The local concentration is that of a colloidal glass. So what you're doing is you're phase separating. The gelation is due to a phase separation, a non-equilibrium spinodal phase separation. You're getting spinodal decomposition into this gel structure and to the structure where there's no particles. And this region here is freezing because you're going into a colloidal glass region. And it's freezing. It's becoming a frozen region of a spinodal decomposition, interconnected network of a colloidal glass. So this is a very simple physical picture of why you get gelation. This is another way of looking at it where we're actually comparing real measurements. But the point is the same thing, that you get essentially a dynamic arrest of a spinodal decomposition, and that's what leads to gelation. And the important point of this data is to show that you get gelation. You cannot get gelation unless you get spinodal decomposition. And this is quite generally true when you have these weakly interacting, not these quasi-equilibrium behavior. That's what the jamming is. That's the nature of the solid formation. Okay, I've covered everything I want. I've gone a little bit over. It's an hour and a half, but that's about what I said I would. I'm very happy to continue and take any questions if anybody has any questions. Otherwise, I thank you all very much for your attention. Do you have reference for the phase separation without gravity? Yes. It's a reference. It's a paper published 5 or 6 years ago in PhysRev Letters. If you look on my website and look, I believe the first author was Bailey, B-A-I-L-E-Y, and it's in PhysRev Letters. If you look on the publication list of my papers, you would find it very easily. And if you can't, just email me and I'll send you the reference. Okay. Okay, Mayun, you're welcome. I'm going to sign off now.